Hi and welcome back. So we are going to continue with the next topic in linear regression. So in our previous lecture, we had introduced the concept of multiple linear regression and how we can use PROC REG to create a model which has one dependent variable and multiple independent variables. Now when we are building a multiple linear regression model, all the assumptions of OLS regression are still valid. And the most important assumption that we need to be very careful about when we are looking at multiple variables is that the collinearity assumption is not violated. Collinearity, as the name suggests, has got something to do with linearity. What it assumes is that if I'm building a multiple linear regression model, the independent variables be independent of each other, i.e. they should not have a high correlation or a strong linear relationship amongst them. The reason being that if I'm building a model, let's say which is y is equal to some function of x. So in a linear regression model, I'm building y is equal to a function of x, and this function is basically a linear function which is beta naught plus beta 1x. When I'm building a multiple linear regression model, I'm building a model which is y is function of, let's say, x1 and x2, and this function can be explained as beta naught plus beta 1 x1 plus beta 2 x2. I'm going to ignore the error function for now, and this is beta naught. And what the collinearity function essentially tells us that x1 and x2 should be independent of each other. Why so? Because if x1 and x2 are collinear or do have a linear relationship, essentially x1 is a function of x2 in that case, and x1 would itself be some linear function, could be, let's call it alpha naught. So let me build alpha separately. Is alpha naught plus alpha 1 x2. So essentially what I'm saying is that x1 is also a function of x2, therefore I can replace x1 over here with x2, and I am still basically building a function where y is a function of x. So x1 and x2, if they are collinear, then one of the variables is redundant. And why it creates a problem in multiple linear regression is because we are using matrix mathematics to actually estimate. So when we have variables x1, x2 till xn, and we have the matrix or a data set as a matrix, and we try to estimate the parameters, which is our beta matrix, which is simply beta 1, beta 2 till beta n. And this matrix multiplication to minimize the error term, this creates a problem if one of the variables is actually a function of the other variables, and it actually will create problems in inverting and multiplying the matrices. So we're not going to go into the matrix statistics part for now, but it violates a assumption of OLS regression. We need to have variables x1 and x2 such that x1 is not a function of x2 or vice versa. So therefore they should not have a linear relationship. It's very difficult to completely eliminate linear relationships because of the first assumption in OLS. So if I look at the first assumption talks about that there is a linear relationship between all independent variables and dependent variables. So if the first assumption holds true, we know that y should have a linear relationship with x1, y should also have a linear relationship with x2. Now if y has a strong linear relationship with x1 and x2, it is quite likely that x1 and x2 will have some linear relationship between them, and that may not be avoidable. However, we need to minimize this. So therefore, we actually keep track of the linear relationship between the independent variables. And if x1 and x2 are highly correlated, or they are strong functions of each other in a linear format, in that case, we will eliminate one of the variables and build a model which has only one of the correlated variables. So for example, let's say I'm going to build a function y is equal to function of a, b, c, and d. These are my four independent variables. And if I look at the correlation matrix, so I build a correlation matrix of these two variables. Obviously, the diagonal will always be 1, and I study the correlation between the four variables amongst each other. I identify that B and D are highly correlated with one another. So in this case, I have a option. Either I build y as a function of A, B, and C alone, or I build a model with y is equal to function of a, c and d. So I cannot have both b and d in my model at the same time, as it would violate my multicollinearity or the collinearity formula. Sorry, the assumption. So whenever we have multiple independent variables, it's always a good idea to look at the correlations between the multiple independent variables and identify pairs which are highly correlated, and remove one of the correlated variables such that the variable which comes in does not have a high correlation with any of the other variables. So that is fairly simple to do, but a problem arises when we have multicollinearity. So multicollinearity happens when we have groups of variables. So I'll just try and explain multicollinearity again. So let's say I have a whole set of independent variables where I'm building a function y is equal to a linear function of a, b, c, d, e, f, g. Let's say these are my variables: 1, 2, 3, 4, 5, 6, 7 variables. And I look at the correlations between all of them, and I see that, let's say, A, E and G are highly correlated. Then C, D and let's say B are highly correlated, and so on. So I have, instead of having 1:1 high correlation, I have groups of variables which are highly intercorrelated with one another. So this is the problem of multicollinearity. So I have multicollinearity, and eliminating multicollinearity becomes slightly more difficult if you want to do it manually looking at correlation matrices, because we'll have groups of variables, and then we have to figure out which of these three variables should I bring in to the model. Should I bring two? Should I bring three? Should I bring only one? And I know these groups of variables are not correlated with one another, and this problem can get compounded with when I have more than, I have multiple groups. Some of them are highly correlated, some of them are weakly correlated, and it becomes a proper mess trying to figure out multicollinearity. So if I have groups of only collinear variables, it's easy to weed out a highly correlated pair and bring only one in. But collinearity does not always come in pairs. You can have, groups of 3, 4, or even 5 or 6 variables highly correlated with one another. Identifying such a group is a major problem itself. So there's one method which we can use to identify collinearity, and that method, obviously, correlation matrix is a simpler method of figuring out collinear variables and removing pairs which are highly correlated. We can identify variables which have, or pairs which have high correlation, let's say 0.5, or you can even use, 0.7 and above, and figure out variables which have a correlation higher than 0.6 or 0.7. I am going to remove one of the two from such a pair and ensure that only one of those two variables is included in my model. However, as I mentioned, it can become cumbersome when there is multicollinearity, and this is where we use a procedure or a statistics called Variance Inflation Factor, or VIF, to detect and remove multicollinearity. So how does Variance Inflation Factor, or VIF, actually work? So VIF factor is a very popular method of detecting multicollinearity and creating a clean dataset on which to build a model on, which does not have this problem. So let's assume again that I want to build a function y is equal to a function of, let's say, a, b, c, d and e. So I have 5 independent variables. I don't know for now whether these are independent or not, whether these are collinear or not. So this is the data set which I'm starting off with, and I want to ensure that the multicollinearity function assumption is not violated. So what we can do with this is we can calculate the VIF for each of these variables. Now I'm going to talk about how VIF is calculated. So let's say I have variables a, b, c, d and e. So when we are calculating VIF, we don't need to look at the dependent variable at all. We only look at the independent variables. So this is a statistic which is calculated only on the independent variables. What we do is, I will train a as a function of b, c, d and e. Right? So I make a as the dependent variable. So this becomes the dependent variable. All the others become an independent variable, and I build a simple linear regression formula or linear regression model on this. And I calculate the R square of A, or R square of this model. So as I mentioned earlier, R square is the percentage variance in A which can be explained by all the other independent variables. For this linear model, so this function has to be a linear model or a regression model itself. I generate the R square for this for this function and see how well are B, C, D and E able to explain the variance of A. Now take a note that if the other variables are able to explain a high amount of variation in A, that would essentially mean that A as an independent variable is redundant because B, C, D and E can capture all the variance in A. Therefore, I need not bring A into the model. On the other hand, if this R square is low, that would mean that B, C, D and E are not able to capture the variance in A. Therefore, A is actually independent of B, C, D and E, and it should be brought into the model as it brings a new perspective, so to say. So once I calculate the R square, VIF is a very simple formula. VIF is simply 1 over 1 minus R square. Now, the R square for this model can range from 0 to 1. So if I put 0 in this, it becomes 1 over 1 minus 0, which is the 1. So the minimum value of VIF min is equal to 1. Now, the maximum R square can go is 1. When this happens, it essentially means that B, C, D and E can perfectly capture the complete variance which A is bringing. So therefore VIF max will become 1 over 1 minus R square, which is 1 in this case. So this becomes 1 over 0. Essentially says it starts to approach infinity. So the range of VIF, it can range from 1 to infinity. 1 essentially means that a variable is independent, and infinity or a higher value means that the variable is actually dependent on the others, or it can be a function of the other variable. So higher the VIF, more collinear is the variable. So lower the VIF, the better it is to if the VIF is low, then we should bring it in the model. If the VIF is high, we should remove it from the model. So this is how I calculate the VIF for A. Now when I want to calculate the VIF for B, I make B as a function of all the other remaining variables. So I bring in A as well. So I bring in A, C, D and E. So this becomes the B as a function of this. I calculate the R square and then I calculate 1 over 1 minus R square. So one particular point I want to make, 1 over R square, 1 minus R square is also called as the tolerance of the model. So VIF can also be called as 1 over tolerance. So tolerance and VIF are interchangeable. VIF is the inverse of tolerance. Tolerance is the inverse of VIF. We don't use the term tolerance too often, but it's good to know that tolerance is simply 1 minus R square. So it's not a very complicated thing to remember. So I calculate the VIF for B. For the VIF for C, I calculate function of C as a function of A, B, D and E. And similarly, D is a function of A, B, C and E. And E is a function of A, B, C and D. So this way I create 1, 2, 3, 4, 5 regression models, and for each of the regression model I calculate the R square and I calculate VIF as 1 over 1 minus R square, and that will give me a number, a single statistic against each of these variables. So let me just pull up a new sheet now. So I'm sorry, just let me get some straighter lines over here. So these are my independent variables and this is the VIF. So I generate A, B, C, D and E. I get the VIF which will range from 1 to infinity. So I get VIF for A, I get VIF for B, I get VIF for C and so on. I get the VIF for E. So VIF is going to be a number ranging from 1 to infinity. So it's a continuous or it's a proper statistic number which is generated. And I look at the VIFs. Higher the VIF, more collinear is the variable. So if the VIF is high, I need to actually start removing the variables from there. So how high? So how high is too high? So let's look at the presentation. So we've already covered VIF is 1 over tolerance. So typically a rule of hand can be applied. VIFs above 5 or 10 So VIF over 5 or 10 can be considered as a cutoff. So let's assume that we apply a cutoff of 10. Now again, this is a rule of thumb. In most cases, 10 or 5 is sufficient to actually weed out collinear variables. But in some cases, it's not unheard of applying VIF cutoffs of even 3 and 2. To get a VIF cutoff of, let's say, 10, so what should be the value of r square? So 1 minus r square, if this is the cutoff of 10, essentially we are saying that this is essentially becomes 1 is equal to 10 minus 10 r square, or 10 r square is equal to 10 minus 1, which is equal to 10 minus 1, which is equal to 9, or r square is equal to 9 by 10, or 90%. So if more than 90% of the variation of the variable can be explained, in that case we're going to reject the variable. And if it's only less than 90%, then we are fine to keep the variable. So that's another way of figuring out what r square is the cutoff for VIF 10. If we replace this with 5, we can solve it and get the r square cutoff for VIF 5 as well. So however, that's not what we want to concentrate on. We want to look at simply the cutoff value. So if I look at the cutoff for 10 and identify that B has a VIF of, let's say, 11, and everything else has a VIF of lower than 10, right? In that case, I can remove B and go ahead with the model. So let's say I have another problem, the highest cutoff. So let's say I have instead of just 11, I have VIF over here as 20, so this becomes 15, this becomes 17, and so on, and this becomes 5. So in this case, what do I do? If I have a VIF cutoff of 10, do I remove all the variables which have VIF greater than 10? So that would be a mistake, because I can't do that in one shot, and I'll explain why. Let's remove this. Let's make some space over here. Back, yeah. So if I want to have a cutoff of 10, right, and I identify that B has the highest VIF, and that's 20, I need to obviously remove B from the model. But do I remove C and A at the same time because they have high VIFs? That would be a mistake, because this VIF has been calculated keeping B in mind as well. So removal of variables due to collinearity by using the VIF is an iterative method. I need to remove one variable at a time. So I remove B and I recalculate the VIFs. So I create another table and I look at the IVs. So now I have IVs which is A, C, D and E, and I calculate VIF over here with the caveat that A is a function of now only C, D and E. I don't keep B in this because B has been removed. Now when I recalculate the VIFs, these VIFs will change because B is no longer in the model for each of these independent variables. Therefore, as soon as I remove a variable, the VIFs for the other variables will also change automatically. So I need to recalculate VIFs when I remove B from my list of independent variables, and again compare with the cutoff. Identify the variable with the highest VIF. If that VIF is still above 10, remove that variable and then redo the process again. And keep doing this process one variable at a time till the time all the VIFs remaining in my independent variable list or set is less than 10. Then I can proceed with building a regression models, and this is how VIF actually works. So quick recap how VIF works. So VIF stands for Variance Inflation Factor. This is a methodology which can be used to detect multicollinearity. So we will detect multicollinear variables and remove them from our modeling procedure. So VIF can be calculated for each independent variable in a regression model. So for each IV in model, create a secondary model with that particular IV as the dependent variable and the other independent variables as independent variables. So as shown over here, we select each variable at a time and calculate it as or create a regression model with that variable as the dependent variable, rest of the variables as the independent variables. Once we have that linear regression model, we look at the r square of that model and calculate VIF as simply 1 over 1 minus r square. So this is how VIF is calculated. So we calculate the VIF for each variable in turn, and then we compare the VIF values to the cutoff. So whatever is our cutoff. So identify the variable with the highest VIF, compare it with the cutoff. If that VIF is higher than the cutoff, remove that variable from the model, recalculate VIFs again, and continue doing this till all variables remaining in my model are having a VIF less than cutoff. So once we've done that, we've solved the problem of collinearity in our dataset, and we can continue with our procedure or regression model. So how do we actually generate the VIF on SAS? So the procedure is simple. I do a PROC REG data equal to dataset name, model, etc. And before the semicolon, I give an option /VIF, and this will generate the VIF table in the PROC REG output itself, and I can study the variance inflation factor. So let's have a look in the model that we generated. So PROC REG model math equal to science, read, write, and social studies on the HSB2 dataset. We got an R square of 55%, and these are our variables. And I can see that social studies is there, and social studies is coming as insignificant. So the p-value is greater than alpha. Therefore, this estimate against social studies is actually insignificant or not significantly different from 0. So that's what this p-value or the t-test is actually conducting. So let me remove this. Let me remove social studies from here, and the syntax says that I just need to do /VIF. So let me do /VIF. In fact, I'll just leave social studies in so that we get so I'll ignore whether the variable is significant or not. Let's study the variance inflation factor for all these variables. Let's open the output and say. So here we have it. So we have the variance inflation as a column added to a parameter estimates. Everything else is the same. We get the same ANOVA table, the total variance in the dependent variable, the variance explained by the model, the unexplained variance or the error variance, and R square is simply the model explained variance divided by the total variance in the dependent variable. So we know that 55% of the variance in math has been explained by the independent variables that we have. We look at the VIF over here. The highest VIF is for read, and as we can see, even with this level of VIF, the variables are not highly correlated, or there is no problem of collinearity because we are taking a cutoff of 10. Even if we take a cutoff of 5 or 4 or 3, it's still okay. So based on this, our dataset does not have a collinearity problem. We do not need to remove variables due to collinearity. However, social studies is a variable which is coming out as insignificant by looking at the p-values. If the p-value is greater than alpha, therefore null is assumed to be true. The null is that social studies does not have a linear relationship with the dependent variable in this case, due to other variables already having explained the variance in that variable. So in terms of multiple linear regression, social studies does not provide us any extra variance to be explained for math when we have science, read and write already doing the heavy lifting. So I can actually remove social studies from here, and still the R square will not change. So if I know the R square right now is 5596, let's have a look here. And we saw it in our last lecture as well. It still remains almost the same. So from 5596 it goes down to only 5546, which is an insignificant change, and our model actually becomes with 3 independent variables. So it's a simpler model and it provides just the same performance. Therefore, it's a better model. So this was how do we test variance inflation factor. So let's try it out with another example. So let's look at the car sales data. So we have car sales data. We've got sales of the model, and we've got parameters such as engine size, horsepower, wheelbase, width, length, curve weight, and so on. Curve weight, fuel capacity, miles per gallon. I want to check whether we can build a model which predicts the sales of the vehicle by looking at its parameters. So let's look at this model. So ODS HTML PROC REG data equal to data dot car underscore sales model. That's the variable name is, so I'll copy out the variable name so that there's no problem. So model sales equal to, so let's look at the independent variable list. So engine underscore size, engine underscore s, then we have horsepower, so it's HORSEPOW. Then we have wheelbase, so WHEELBAS. Then we have width, so let's look at width. Then we have length, let's look at length, TH, LENGTH. Then curve weight, so CURB underscore WGT. I can actually do a proc contents and copy it out, but let's finish it this way itself. Fuel capacity and MPG. And I want to look at the VIF as well, so that I don't have any collinear variables. And let's run this model and see what it looks like. So there's an error over here. Let's see. Okay, MGP not found. So I made a mistake. It's not MGP, it's MPG. Let's run it here. And we've got a regression model out. Let's see what is the variance in the total sales we are able to explain by all the independent variables that we have. So let's see, 153 observations over there. The ANOVA tells us that the p-value is less than alpha, i.e. at least one of the independent variables has a significant linear relationship with the dependent variable. Therefore, the regression is significant. So this is the first thing that we want to check. The regression is coming out to be significant in our case. And the total variance in the dependent variable is this value. We are only able to explain this much. Error is huge. So I look at the R square and yep, R square is only 31%. So only 30% of the variation can be explained. But that's fine. We are not looking to build a earth shattering model here. We are simply looking to study this model. And let's look at each of the variables in turn. And let's solve the collinearity function first. And I want to keep a VIF cutoff of 5. So if I look at the VIFs over here, so I see engine size is greater than the cutoff, curve weight is greater than the cutoff, i.e. they are very highly collinear. And based on this, these two variables are very collinear and need to be removed. However, I can only remove one variable at a time and check the VIF again. So which variable do I remove? I can remove the variable with the highest VIF alone, so I need to remove curve weight. So let's go back. I'll copy this and say removing curve weight due to high VIF. This, and let's remove curve weight. Let's build the model again. Let's look at the data set, and there's the model. Yeah. So you will observe that the R square has gone down, but we're not bothered with R square as of now. We need to remove collinear variables. So R square is irrelevant. So even if I get if my R square goes down by removing collinear variables, that's fine because that R square was inflated as it is. So that's why it's called variance inflation factor, because it inflates the variable, it inflates variance, and that can give us erroneously high R square. So that R square was not a stable R square. So even if R square goes down by removing collinear variable, that's of no concern to us. Let's look at this. I see that engine size is still higher than the cutoff, so I'm going to remove engine size as well. So let's go here. It's removing engine size due to high VIF, and we look at this and remove engine size and run this again. So let's see. PROC REG procedure. There we have it. So the R square has gone down to 23%, but now if I look at the VIFs, they're all fine. There's no problem over here. So now let's start looking at another problem, that each of the independent variables. So our next assumption that we have to take care of is that there's a linear relationship between each independent variable and the dependent variable. So let's look at this again. So I see a lot of these variables have alpha p-values which are greater than alpha, i.e. they are not relevant, or the estimate is not significantly different from 0. So let's have a look at this. Identify the so again over here we must add or remove one variable at a time. So we should not just remove all variables which have p-values greater than alpha, because there might be a lot of interaction going on. So identify the variable which is the most useless in this regression. So that would be the variable with the highest p-value. And if I look at this is the highest p-value, 0.97, almost 1. So I know that length has got absolutely nothing whatsoever to do with the sales price. So let's remove length. So I'm going to go ahead and removing length, since it is insignificant. And let's run this again. I'm going to copy this, place it here, and delete length. So I know when I ran it with length in the model, the R square was coming out to be 23%. So if I remove length, and I know that length is insignificant, therefore my R square should not change by too much. And let's have a look. And there we go. R square is still 23%. And oh, right, I'm looking at the wrong output. So let me open this output again. Yeah. So I see R square is again only 23%, still 23%. It's not changed, but I've removed length from my model. Now identify the next highest p-value, width. So we can remove width as well. It's got nothing to do. So let's remove width. Removing width from model due to insignificant relation. There we go. And I want to delete width. Width is also gone. Let's open the latest regression. So as you can see, building a regression model is not so simple as just running one PROC REG. It's actually an iterative procedure. You have to follow a lot of a whole lot of tests onto this. And let's see. So width has been removed. My R square is still 23%, and I don't expect it to change too much, since I'm removing variables which don't provide any help to in the model as well. So I see miles per gallon also is next to be removed. Let's move on. Removing MPG due to, let me just copy this insignificant relationship with, and I'll copy the PROC REG procedure as well, and remove the MPG variable. Let's have a look at this procedure result now. There, so it's still 23 or 22.94, so it's very slight change but insignificant over here. And we've removed the with MPG as well. And finally, the last variable that we need to remove is fuel capacity, hopefully. And let's remove fuel capacity as well. So removing fuel cap, and let's run this model again. I've deleted fuel cap. I'm running it with sales equal to only horsepower and wheelbase, and there we have it. Sorry, this is the previous model only. And that's my final model. So 22.5% of the variation that we can explain. I've got two variables in my model. Both of them are significant, and more importantly, they are not collinear with each other. So if I have only two variables, the VIF for them will be the same, because the R square of horsepower to wheelbase and wheelbase to horsepower will be the same, because the correlation, which is R, doesn't matter if I take X correlation of X with Y or Y with X, the R remains the same. Therefore, R square will also be the same between these two variables. Hence, VIF is exactly the same. And both of these variables have p-values less than alpha. Therefore, they are highly significant linear relationship with the price sales, and that's a final model. And obviously, what we've done is we've used a VIF cutoff of 5. If I use a VIF cutoff of 10, we would get a slightly different model. So what happens if I use a VIF cutoff of only 10? So let's look at our initial model that we started off with. And so this is my initial model. Yeah, let me just open it again. So this was my initial model where I had an R square of 31%. And if I had a VIF cutoff of 10, I would not have removed any of the variables due to the VIF cutoff, but I would have still gone ahead and started removing variables like width, fuel capacity, miles per gallon, etc., because they were insignificant. And in this case, it wouldn't have mattered. I would have still gone through all of the variables, but maybe I would have retained engine size, because it has a significant relationship, and other variables as well. So depending on what my prior assumptions are and what are the cutoffs that I'm operating in, different modelers or different analysts will come up with different kinds of models. So some of them might want to maximize the R square, whereas some of them might want to minimize on the deviations from the assumptions of OLS. So again, what we need to do, or rather the procedure is that we should not get too hung up on building a model which is statistically valid, because these models are going to be implemented in business. So a model should make more business value, and that should be our concern, rather than making sure all assumptions are met. So while assumptions are there, and in academic models it makes sense to make solid stable models, but in business, assumptions or violation of assumptions is something that you can still go ahead with, as long as the end result creates business value for you. So that is what actually drives VIF cutoff. So while 5 may be excessive, because what's happening is when I use a VIF cutoff of 5, I actually remove variables which is driving down my R square. So I have a R square of 31%, and I finally select a model which has a R square of around 22%. However, if I leave these variables in, I can still get up to 30% of VIF, the variation explained. And but I will have to live with a little higher collinearity than I may be comfortable with. So again, there's a give and take over here. There is no perfect model as such. So this was an example of the variance inflation factor. So in our next lecture, we're going to talk about bringing nominal variables into regression.